Hi everyone, thanks for opening up your science sketchbook. In this video, I'm going to show you the most important tips to find accurate resonance structures and how to pick the major structure. Stay until the end for some practice questions. So I'm going to show you 4 major rules when it comes to making resonance structures. Remember, resonance structures are just showing the delocalization of electrons in a compound. So to start, you can only move electron-related pieces. This fundamental rule talks about what can change and what can be moved around in a resonance structure. You're just looking for lone electrons like these highlighted, pi electrons, such as this double bond, and charge symbols, because as you move electrons around, the formal charges may swap in some places. The reason why only available electrons can move is because, well, if you move atoms around like in this molecule here, you now get a constitutional isomer. This is still C4H6O, but the connectivity is different. This is not the same as a resonance structure. If you move atoms around a lot for some reason, you could even get a totally different compound. Notice how this one has 2 extra hydrogens. It's C4H8O. So make sure your molecular formulas don't change. So if you're unsure, look for things like these as a possible starting point. That leads us well into the next rule. You can't add or remove any atoms. So we already saw that drawing the molecule wrong can change the molecular formula. But another thing to consider is that the hydrogens you start with should be exactly where they were across resonance structures. Don't mess with the hydrogens. People often try to fix the molecule to fill an octet by just adding a new implied hydrogen. So just don't do that. See in this example, I moved this double bond to the vacancy, the positive charge. Now, with the hydrogens in view, you might notice, oh, that carbon only has 3 bonds on it. And so a common mistake I see is, well, students will just try to fix the molecule and add a hydrogen to fill that void. Do not do this. It is okay to make a molecule less stable when finding resonance structures. This just changed its molecular formula. The goal of resonance isn't to form the most stable option or something, it's just testing what those options are. So if you formed a vacancy, just put the vacancy sign there, the cation. You can move charges around, but you can't add new hydrogens. Keep the same exact ones as you had in the beginning. So that takes us to the next rule. You must conserve the overall net charge of the molecule. Look at these 2 resonance structures we just formed in the last example. When we formed that vacancy on the right, it allowed us to maintain the overall neutral charge of the molecule. If I forgot to put that positive there, the molecule on the right would be negative overall, with no positive to balance it out. We can form another resonance structure to check it out. If we move the electrons up here towards that vacancy instead, you get this molecule here. Both charges canceled out in that move, the formal charges both became 0, and that's perfect. This leaves it at a net charge of 0. It doesn't have to show a literal +1 and -1 just like the original, it just has to be neutral overall. The next rule is the major idea to keep in mind with resonance. You cannot exceed octet rules. You can only form molecules that are physically possible, but you can go below the octet. Usually when students ask me about resonance, I get the question, what do I even move first? This rule will help you with that choice. Ultimately, I recommend you really just try moving anywhere. Ideally, you can first search for a vacancy or a carbocation. If you move towards that charge, no octets are broken because, well, there was an opening, a vacancy, and you can just swap the charge over. If you weren't sure if that's the only starting move or if there was no charge from the beginning, I suggest you start anywhere and test it out. You may be able to form a new vacancy, or you will notice, if it's not physically possible, it's not physically possible. This is what I mean by test the octet. Make sure you know where all your hydrogens are and how many bonds are on an atom, and you'll discover moves that are not possible. See in this brief example, I tried passing that pi bond over to oxygen, but oops, no, oxygen has 10 total electrons now. It can't do that. Thus, our original move was the correct choice. So yeah, don't know what to move first? Try to gravitate towards a vacancy or a carbocation, or just literally start anywhere and test out moves until you find ones that don't exceed the octet. Let's see one more example, but in this one there is no vacancy from the beginning, so no clue of where to start. Here's a molecule. Well, when in doubt, test it out. Drawing in your hydrogens really helps you see what is a possible move. So try moving that pi bond to the left there. What do you think? Is this a fine move? Oops, no, this carbon here has 5 bonds to it now, or 10 total electrons. That's not going to work. How about this move? Let's test it out. Look at this structure. Does this one work? Yeah, the oxygen is still at a full octet. Its formal charge is just negative now, and that just happened because the double bond stacked as a lone pair on the oxygen instead. The carbon is now below the octet. It has 3 bonds only because, as you see on the left, there was no hydrogen there. So it's just got a positive formal charge now. Carbon isn't super happy about it, but you are totally allowed to make the molecule a little uncomfortable as long as it is physically possible. Once again, the goal is just to find a resonance structure, not necessarily the best one right away. So, those are the 4 major rules you can consider for forming a resonance structure. Only moving electron-related parts, not adding or removing any atoms, basically keeping all hydrogens exactly where they are and other atoms, conserving the overall or net charge of the molecule, and not exceeding the octet. Let's try one together. We can find some resonance structures of this molecule here. Remember, to begin, my recommendations were to move towards a vacancy or a positive, or test the octet. Since there's no positive here, let's test a move out. Which arrow do you think we should follow? Yeah, none of those work. If I move the lone pair into a double bond like the red arrow on the left, that carbon that is double bonded to oxygen will have 10 total electrons, exceeding the octet. The same goes for following the orange arrow to the right. If you didn't notice that the octet is broken, remember to draw in your hydrogens. The original molecule already has 3 on that carbon, so adding an extra bond in that direction would put the carbon at 10 total as well. The same goes for that blue arrow downwards. Those hydrogens fully occupied the space, so 1 more bond would exceed the octet. So, as you can see, don't push extra electrons onto a full octet. But look at this move. You can stack double bond electrons onto an atom that already had them, making the bond into a lone pair. This is super typical of CO double bonds, for example, or carbonyls. To verify, you can see the oxygen is still at 8 electrons total, and the carbon is now below 8 electrons, which is fine. It's not breaking any rules, it's just a bit unhappy with that. So, that's a viable resonance structure, right? Oh, what are we forgetting? The charges, right? You will likely get used to what charges should appear, but if you're unsure, find the formal charge. Using the quick method for formal charge, for oxygen, 6 valence electrons minus 1 stick and 6 dots is -1. For carbon, 4 valence minus 3 sticks and no dots is +1. Add those charges on and this is perfect. The original molecule had an overall or net charge of 0, and this one with a plus and minus that cancel out also has a net charge of 0. So we conserve the charge as expected. So this is a full, accurate, and possible resonance structure. With the new vacancy on the carbon, we can now move those electrons from nitrogen over into a double bond. Remember, we previously couldn't because the carbon had a full octet and couldn't take any more bonds. Now, it's open. If you pass those electrons over into a double bond, it looks like this. Where did that positive go? We can't just get rid of it, right? But hey, check over here. The nitrogen now has a formal charge of +1. Now it is all set. At this point, is there anything else we can move? We already worked with the lone pairs, pi bonds, and charges, so unless you go backwards to the original again or make double bonds into lone pairs on carbon, this is pretty much it. Great job. Now, just to throw this in there, what if you were asked about the major contributor to the resonance forms? Remember that resonance structures are just this theoretical idea of where electrons are kind of spread out in a molecule. Well, when you're asked for the major contributor, you're just being asked for the most stable structure. That could be a whole video in itself, but we can take a look at 3 major signs here. Honestly, this will usually answer the question for you. So 1. Which has all atoms at a full octet? Check it out. The first and last ones both have all their atoms at full octets, regardless of charges, but the second one has a carbon below the octet. So already, you can see which is likely the worst structure. Another question is which has less formal charges? Basically, less charges scattered around in total and in value. You wouldn't want a +2, -2, for example. The first one is the only one with no charges at all. The cleaner it looks, the more stable it tends to be in resonance. And one last signal to look for is which structure has the charge off of carbon. So organic chemistry is all about carbon, and it's picky and does not want to hold that charge. Any other atom would rather take the charge than carbon. So the first and third are the only ones that do not show a charge on a carbon. Keep in mind, if the molecule is like all carbons, or there is literally no way to get the charge off of a carbon, then you can use carbocation stability rules, like a tertiary carbocation being better than a secondary or primary. Again, another topic for another video. So, with all those rules, I think there is a clear rank in terms of who is most stable. The worst one is the middle one. It did not satisfy any of the stability trends. The next one would be the one on the right. It was pretty good, but it did ultimately have those charges scattered about. And finally, the best one is the first one. All filled octets, no charges, and no charge on carbon. I know it'll take some practice, so let me give you a brief overview before some questions. We covered a lot, so to recap, use those 4 resonance rules to guide your arrows. Remember, that was concepts like only moving electrons, not adding atoms, conserving charge, and not exceeding the octet. Next, if you don't know what to move first, try to move electrons towards a vacancy like a carbocation. Otherwise, test moves by checking the octets to see what's possible. Finally, the 3 main signs of resonance stability to pick the major contributor to the overall form, those included all atoms with a full octet, less formal charges, and a charge off of carbon. So if you don't find this topic very easy, don't worry, it's not. So let's try to practice a little. All right, so draw resonance structures of the following, then find the major contributor. Sketch the Dog suggests you pause the video here to practice. Alrighty, let's see how you did. Here are resonance structures for the first one. Check your work with mine and let me know how you did. Now, with the arrows and hydrogens out of the way, take a look. Which one did you pick as the major contributor? Yeah, that last one. Full octets and only one charge, just like the first one, but instead the charge is off of carbon and on that oxygen. Much better. Let's see that next one. Here it is. Hopefully you remembered that nitrogen had a lone pair. You wouldn't be able to just assume that nitrogen was just lacking electrons, especially since the nitrogen didn't have a charge initially drawn on. So, if you move those lone pairs, you get these, and yeah, here they are. Good so far? Now with everything out of the way, yep, the major contributor happened to be the last one on here too. Got that charge off of carbon once again. All right, that was a big topic. It's not the easiest concept, but practice is the best way to learn this one. If you want to learn more, subscribe to my channel for more organic chemistry tips, and check each playlist for related topics. If this helped, feel free to like the video, and I will catch you in the next one. See you!